Now I would like to say welcome to Esben Larsen, and he will give a speech about the roadmap for local implementation of REN in isolated power systems. Are you there, Esben?
Yes, I am.
Good.
I hope
welcome.
You can see me.
We can see you, yes.
And hear me.
And hear you as well, yes.
And now I'll try to share my screen so that I can do my speech. So hopefully you should see it right now.
Here we go, yes, it's here.
Okay.
Full screen. Yes.
And then then I would have full screen too. Yeah. So I hope it's good for you. So yeah, thank you very much for the opportunity to share my experience in isolated systems. I've been working in this field for the last 10-20 years, especially in Greenland. So it's a pleasure for me to present some of my experience for that period and how to implement different types of renewables in small systems, which are very used. I think most of the audience here is working in this field, so I think you're quite familiar with a lot of these problems and topics which I will face in my presentation. I will give a short introduction to the fundamentals in this area and then the roadmap in these 5 steps. And it is a sort of recommendation how to make investments in this area and get the best benefit out of the investment. It has been a discussion of how to save money, etc. And so I think it fits very well in relation to the last speakers. First of all, an isolated system, what is that? All systems, electrical systems, are isolated, so therefore there's not a clear definition of an isolated system. But when I think of isolated systems or off-grid systems, it's small systems where we do not have industry and heavy loads, etc. Typically, a sort of power production from renewables, perhaps a diesel genset. We have typical households as consumers, and we could introduce a storage or not. So it is these rather small systems which I am facing in my contribution here. I'll come back to the balance. Hybrid systems in general, if we just look at a diesel genset system, then of course no renewables. We could introduce more or less renewables, let's say 25%. Typically it will be without a battery, and if we increase that, then we can introduce a storage battery and have a better performance of the total system. And the most challenging will be if we do not have a diesel genset. So it's a sort of more or less renewables in such systems. And I've experienced from different locations here, which I will give a reference to later on. First of all, I will talk about power balance and energy balance. If we are looking at power balance, it means that we must have balance between production and load second to second. And it gives, especially for these small systems, problems if we have larger machines, etc., because we have a large inrush current, and it can cause trips for such systems. This stability problem. I will not face that in my contribution, but only look at energy balance, where we have, it's the same equation that production must be equal to load. And if we do not have this equilibrium, then we will have problems related to the frequency in the system. We can introduce a battery, and in that case, as you see here, then we can discharges or charges depending on if it's a load or a source. So when we are talking about energy balance, then we normally look at hour by hour estimation, and it was which I will look at here. So it was this very short introduction in background. Then I will continue with these 5 steps in how to introduce renewables in small off-grid or isolated systems. First of all, then you must look at energy savings, because the cheapest kilowatt hour is the kilowatt hour not produced. So is there any possibilities for reducing your load? Then do that first before you are investing in renewables. And here's a list of possibilities. Light, it could be LED, inductive heating for cooking, cooling systems, heat pumps, efficient rotating machines, etc. Go through all your system and see, is it possible to make energy savings before you are investing in larger or wind turbines or PV in your system, or especially batteries, which are rather expensive. Then the next step is to make a good load estimation. And it can be a hard job, because it requires at least some detailed measurements. But if you make a daily curve, then you can have some assumptions on how it will be developed over the year. But typically we can look at a daily consumption and make some estimations because we have experience from how the load will change over the year. But first of all, here we have an example of the daily load curve from Vejrø, a little island south of Zealand, where we have an isolated system. And there's not very much different between the maximum load and the minimum load during the day, but during the summer period, at this location here, we have a factor of 2 or something like that. But typically, try to make a good estimation hour by hour. It means that you will get 8,760 measurements or estimates over a year. Then, if we are looking into to wind turbines, then making wind estimations, and an earlier speaker discussed how to make wind estimations in a cheap way. Normally, we wish to have wind measurements over 3 years, and of course, if we are a large investor, then I think I would prefer to use accredited measurements. But if we are in these small communities, then perhaps we do not need accredited measurements for as well the wind and the specific wind turbine. But if this is not available, then we can get data from Meteorological Service Organization, DMI, NASA, and other sources, where we can estimate our wind at a specific locations. When we have these data, then we could use different simulation programs. WASP is developed at Risø, and it one of the tools. You put in a lot of data, and then you get one specific result, the annual energy production, based on a specific wind turbine and a specific location, where we have taken the local area, trees, houses, etc., into account. The other thing is also for the investment in a wind turbine is the installation. What will be the cost of that? Be the transport of turbine, foundation, distance to power system, cable protection, etc. So this must be taken into account before we can look at wind turbines. Here's some extra considerations which we have done in relation to selection of the wind turbine. Of course, the expected production from the wind turbine based on a power curve, stability, size of the wind turbine compared to the diesel genset. If we have a large wind turbine, it can give instability. If we have a small wind turbine, as I will show you an example of in a moment. Do we expect extreme winds at the specific location? Then it requires some extra specifications for the mechanical structure of the wind turbine. Do we choose a stall or a pitch regulated wind turbine? The generator type. If, as I have looked at here, the Arctic temperatures, it can give an influence on the operation of the system. Also, the location of the electronics. The electronics are normally not rated for very low temperatures below -10 degrees. Color blades, white, black blades. There the ice will melt more fast compared to white blades. Installation, foundations, distance to power system, cable protection, and maintenance. Of course, do we have maintenance persons at the specific locations, or is they unexperienced? My proposal and recommendation is keep it simple. But of course, the decision is yours, but you at least here you have some points to check when you make your selection of a wind turbine. I have experience specific for Savanguak, a wind turbine, 6 kilowatt. It was a proven wind turbine. I don't think it's produced any longer, but it was rather good for that location. I'll not go into the details of the wind turbine, but we had at that location a risk of high wind speeds. Therefore, we added these gay wires. We did not have electronics in the wind turbine, nothing at all. The cables to the power stations is put on the surface of a rock in half tubes. We had a half kilometer to the power station where we have the inverters with the electronics. The installation, it was made by a helicopter, which could hoist this up to this top of the mountain, 77 meters above sea level. We have not seen any change in security of supply for this little community. We have had large temperature changes, especially low temperatures, but we have not seen any problems. No icing have been seen, but some noise. The production level was much lower compared to the estimated because of some stability problems in the inverter system. We needed a monitoring system and a communication system. It was a absolutely a challenge in Greenland at that time. It's much better today. So it's a point at least too. But the total installation cost for this system was pretty high. If we are looking at PV as an alternative, then we come more or less through the same process, estimate the irradiation. It can be made by measurements or data from meteorological service organizations. It's some of the same sources as we have used from for wind, if we did not have own measurements. They are in the same way there exists simulation programs, PV Sol, as we typically have used, but it's not especially good for Arctic locations. Then considerations about how to install, roof, rack mount, distance to inverter, cable protection, and the direction of the system, and the tilt angle, of course. In the same way, these considerations for selecting of a PV system, type of PV cell, we have this negative temperature coefficient. It is helpful, especially in Greenland, where we have low temperatures, so it gives a higher production. Then if we can place the system so we can utilize the Albedo effect, it can give up to 3–4% more over a year. The system is fragile in relation to wind, snow shedding, vandalism, which is a problem in Greenland. Of course, installation and mounting system is an issue, and but also we can expect long lifetime, independent of the low temperatures. But it's simple to integrate in a system, and it's easy to combine with a storage technology. PV cells, different types. The cost of these is more or less related to the output, the production. So I will not go into that. This experience from a Sisimiut, it's this house here where we installed a PV system. And there we utilize the Albedo effect because we have a rather large lake in front of the house. We have a tilt angle of 45%. It means that snow and ice more or less will roll down the surface. And as soon as we get some irradiation, this little snow or ice will melt. It means that we have a rather good production. We recommend a tilt angle at least 45%, because if it's lower, then we can have snow over all the PV, and then the production will of course be zero. It's easy to integrate, expect long life, and what we can see here is from 2013, where we have a full year production, 7,648 kilowatt hours for this system of a little more than 7 kilowatt. It gives a thumb number, 1.08 kilowatt hour per watt peak. It's pretty good. It's better than in Denmark, where we typically will have 0.85 to 1 kilowatt hour per watt peak installed. So it means that we have a higher production in Sisimiut compared to Denmark, South Denmark. But of course, the power will be produced over the year in a little other way compared to in Denmark. So the production during the January and November and December will be very low. Still, keep it simple. The system design How large a PV? How large a wind turbine? We have used Homer as an example. It's a rather good simulation program where we can introduce the gensets, the size of that, and let the system optimize to get the best economy in our investments. So I will just show you that it's by use of this simulation program, then we can get how much the different types of wind turbines and PV and gensets will run during the year, and how much they will produce of the total needed load. And here also the excess of electricity. It means that the battery is full charged, and so we cannot get rid of the produced renewable, and of course the gensets will be set to 0 in that case. If we, because where Homer is a very black box, then you can also use Excel or other vector-oriented programs, MATLAB or others, where you more in detail can see what's going on. And here's some example of that by use of these time series for your load, put that in a vector, and you can, in the same way, expectations to the production of wind and from PV. Then you have the possibilities for production from renewables, and you have the loads, and then you try to set up a control strategy for the system. And in this way, not as Homer, but in this way you can see in detail, hour by hour, how your control strategy will control the system. And it depends on if you can change a little on your control strategy, then you can get a better performance of the total system of the same investment. And here's an example of how we can see that here's the load, the yellow one is negative, and the wind turbine and the genset and the PV is gray. It's some days where the PV is very low, and then because of the battery, we can see it must be charged or discharged, and SOC, the state of charge, must be between 20 and 95%. And we can see how it goes up and down, and how the system will act with this control strategy when it's needed to start the gensets 1 or 2, and how the production from the wind and the PV contribute to the balance in the system. So it's a rather good way to see in details how a control strategy reacts, and how you can optimize your control strategy. This was shown by this setup here, that the diesel gensets over a year will produce 22%, the wind turbines 60%, and the PV about close to 20%. So we are very close to a full renewable system. It is for a simulation at wire. It means that we can conclude that different situations of diesel, it will give a reliable and good system. We could more or less introduce a little renewables, 25%, as we've seen in Safanguaq and Sisimiut, without introducing storage batteries. If we will have a high share of renewables, then storage batteries are needed. We have a situation in Ialiku in Greenland, and finally at Vejrø, where we have the possibility to stop the diesel gensets and run totally renewable. But if we run into problems with not covering the load, then we can start the diesel gensets. So it's still a safe system for the inhabitants and the customers at the island. So it was a very fast presentation of different types of isolated systems. I hope some of you will ask some questions to when we can go into this area. Thank you very much for your attention.
Thank you very much, Esben Larsen. It has been really a pleasure and really interesting speak you had. Of course, there will be a lot of questions to you, I think, and to the whole session 3 here, the challenges and potential of wind energy in the Arctic region. One thing I think about is, what about the lubrication for the small wind turbines? It can be extreme cold in Greenland, I know. And did you have any problems about the lubrication?
This wind turbine here has been installed and run more or less without maintenance year by year. It means that it should be have a maintenance process every year, but because we are a university with very low budget, therefore the first couple of years then I was there annually, and then we could make this maintenance. This is a procedure going through, including lubrication. But after some years, then we did not have the funding for going there, and then has just been running. But because of some problems not in the mechanical system, but in the electrical system, then it was just running freely without loading.
Okay.
But so it's a long story, but we have not seen problems with lubrication, especially.
Well, the reason why I'm asking is that on this webinar, there's a lot of manufacturers who are actually very interested in also supporting the Arctic region, and it's important for them also to know, are there special conditions? But I think you have done a very good study here. We are a bit short backward in the schedule, but are there questions here? Otherwise, we will take it. Then otherwise we'll take it after the before the next session in the end of this session. But are there short questions right now? Otherwise, please write them down, and then we'll continue with the next.
Yes.
Yes, there was one.
Yeah. I have one small question. Yeah. So how was wind measurement done in that location?
We have made some measurements based on a met station, a mast over. Now I cannot remember it in details, but we have made some had a met mast close to the location in some years in advance. So we have had a pretty good wind measurement over the year at this specific location. We discussed very much how and where we could place the wind turbine. We ended up with a location close to the antenna of the communication system for this location in Safanguaq. So it is a little small hill, but there was a kilometer from there. There was a better location because there the height was 22 meters instead of the 77 meters. But then, of course, how to install, we needed a cable, not just half a kilometer, but in that case it would be 1.5 kilometer. Then we also had how to install it. How could we come up at that mountain? There's no roads, no paths at all. So we discussed if it was possible to come there in the wintertime with snow sledges, etc. But then this special opportunity to get some helicopter hours because of some construction work for a power line 30 kilometers from there. So it was easy for us to hoist these 1,000 kilograms up at this top here. But there was a lot of practical issues which we took into account to select this specific location.
Okay, thank you.
Thank you.
Well, thank you, Esben, and I hope that you stay with us.
I stay there. Yeah.
Very good.